So next is Johnson counter or twisted ring counter. So in Johnson counter, the difference between Johnson counter and a ring counter or a ring counter and a twisted ring counter is that here we are considering 3-bit. So in a ring counter, if you had D2, D1, D0 as the flip-flops, this is D1, Q1, this is D0, Q0. It's a synchronous counter. So this much it's the same. In ring counter, you connected Q0 to D2. So in Johnson counter, you are connecting D2 to not Q0 but Q0 dash. Okay. So and the initial state is 0 0 0. So Q3, sorry, Q2, Q1, Q0 is 0 0 0 for clock 0. So how do you set that? By making all the clear equal to 0. So here you have clear, here you have clear, here you have clear. So all the clear you are giving to logic 0. And all the preset you are giving to logic 1. Okay. So initial state will be 0 0 0. So here you have a 1, right? So that one comes here. So in the first clock pulse, that 1 will come here. This 0 will come here. This 0 will come here. That is, here again you have a 1. So Q0 dash will come here. That is a 1. This 0 comes here. This 0 comes here. Again Q0 dash is 1. So that 1 comes here. Q2 will come to Q1. Q1 will come to Q0. Q0 dash is again 1. So this is 1. This 1 comes here. This 1 comes here. So Q0 dash is 0. So here you get a 0. This one comes here. This one comes here. So Q0 dash is again a 0. So 0. This 0 comes here. This one comes here. Next clock pulse, Q0 dash is again 0. So 0, this 0 comes here, this 0 comes here. So we have started with 0 and we ended with 0. Okay. And if you give another clock pulse, this will repeat. So this is the difference between Johnson counter and a ring counter. In a ring counter, LSB flip-flop Q is connected to the MSB flip-flop D. In Johnson counter, LSB flip-flop Q bar is connected to the MSB flip-flop D. Okay. In ring counter, you are giving either 100 or 001. in the case of 3-bit ring counter. In case of Johnson counter, initial state is 0, 0, 0. Okay, so that is the Johnson counter. So if you are to draw the timing diagram, you have the clock, okay, this is clock, and you have Q2, Q1, Q0, negative edge, yes. So initial state is 0, 0, 0. Next will be Q0 bar will come here 1, this 0 comes here, this 0 comes here, Q0 bar, this one comes here, this 0 comes here, Q0 bar, this one comes here, this one comes here, Q0 bar is 0, 1, this one comes here, Q0 bar is 0, this 0 comes here, this one comes here, Q0 bar is 0, 0, this 0 comes here, this 0 comes here, Q0 bar is 1, 0, 0, okay, Q0 bar is 1, so that is repeating. Okay, so to draw so in this case, this much is 1 from here to here is my one output cycle. Yes, this much. Or if I am considering Q1, it's from here to here. So how many clock cycles correspond to one output cycle? It is 1, 2, 3, 4, 5, 6. So one output cycle equal to 6 clock cycles. Okay, so 1 by F output is equal to 6 by F clock. So F output equal to F clock by 6. Okay, so the output frequency the frequency of the output is input clock frequency divided by 6. So the input clock frequency is divided by 6 in this particular case. Why 6? Because you used 3 flip-flop. So what's the relation between 3 and 6? It is 3 into 2. So you can say that generally this is 2n, where n is the number of flip-flops. So the frequency is divided by the input clock frequency is divided by 2n, where n is the number of flip-flops. Okay, so this is also called as modulo 2n counter. Modulo 2n counter means the input clock frequency is divided by 2n. In the case of ring counter, it is modulo n counter. Okay, so that is the difference between a ring counter and a twisted ring counter.